Hello everyone and welcome back to my channel Gyan Sampada. In our today's class we are going to deal with a special concept of magnetism which is having a special magnetic order. So let's get magnetized with respect to this new magnetic order. So till our previous classes we have dealt with ferromagnetism and antiferromagnetism. So all details, theories and each parameter we have understood, including the susceptibility and the transition temperatures. And today we will magnetize our focus onto the concept of ferrimagnetism. So what actually is ferrimagnetism is the question. Broad details about ferrimagnetism will be dealt in today's class, and later on in coming classes we will study about the transition temperature as well as the susceptibility. So if you look at this name, it consists of two words. One is ferri, another one is magnetism. When we say ferro, it means there exists ferrum in the material, that is iron is present in the material. Or generally we can say that the material which was found to be ferromagnet was magnetite which contained iron in it. That's why such materials are named as ferromagnets. But how it is different from ferrimagnet is the question. So ferri, is it related to ferric, that is another oxidation state of iron, or something else? That is what we are going to make clear. So in today's class we will be dealing with the history of ferrimagnet, which will be extended to the concept of ferrimagnetic order, that is how magnetic moments are arranged in these material, and finally we will understand about the nature of ferrimagnetic material. So this will be a general discussion on the characteristics of ferrimagnetic material. So first we will start with the history part. So when we go back to the 12th century, until 12th century, whichever magnetic material or substances were observed, those were just called as ferromagnets. There were no special differentiations between the magnetic materials. But later in the year 1936, Lewis Neal, he published a paper proposing the existence of new form of cooperative magnetism, that is the cooperative phenomena, which he called as antiferromagnetism. So already the concept relating to ferromagnet and antiferromagnet is clear in our previous classes, which you can check in the playlist section named ferromagnetism. So in ferromagnets we observe that magnetic order, that is magnetic moments are equal and parallel to each other, whereas if you go for antiferromagnetic material, then the moments are equal and anti-parallel to each other. So this was the new concept proposed in the year 1936 by Lewis Neal, who was a French physicist. So as such, now there were two current concepts. One is ferromagnetism, another one was antiferromagnetism. But later, while working with Mn2Sb, another French physicist named Charles Goulard discovered that the current theories of ferromagnetism as well as antiferromagnetism were not able to explain the behavior of this material. And to explain the behavior of this material, he just proposed another model, which was called as Goulard model. And later in the year 1948, again Lewis Neal published another paper about the special type or the third type of cooperative magnetism, which was based on the assumptions of Goulard model itself. And he called this cooperative concept of magnetism as ferrimagnetism. So names are almost similar, which we can understand based on the nature of magnetic moments. And for his work in magnetism, in the year 1970, Lewis Neal was awarded with Nobel Prize in Physics. So this was a huge contribution from Lewis Neal in the field of magnetism. This is a brief history about ferrimagnetism or entire magnetism. So we can say that ferrimagnetism concept got its name or existence in the year 1948. And now, after knowing the history, let us understand about the ferrimagnetic order. That is, what is the nature of magnetic moments or spins, whether they are equal or unequal, parallel or antiparallel, or whether they are random. So all these factors we are going to cover in ferrimagnetic order. So if you just compare it with ferromagnetic material, in ferromagnetic crystals, saturation magnetization, that is the maximum magnetization which occurs at T is equals to 0 Kelvin, it does not correspond to parallel alignment of magnetic moments of its constituent paramagnetic ions. And this is the case in many of the ferromagnetic crystals. And even in the crystals for which there is a strong evidence that individual paramagnetic ions have their normal magnetic moments only. So to understand, if you just take an example, that is the most familiar example, which is magnetite, that is Fe3O4, which can be written as FeO, Fe2O3. So here we can observe in magnetite both ferric and ferrous ions are present. But earlier magnetite was considered as ferromagnetic material, and now let us see whether it is ferro or ferrimagnetic material. So when we write like this, we can understand that it is having some speciality in its order. So to check it, we need to go for some calculation part, for which we consider its spin and orbital moment. So when we consider the spins of ferric, it is having spin equals to 5 by 2 with 0 orbital moment, which means that each ion should contribute phi mu b, that is mu b is the Bohr magneton, to the saturation moment. And if you consider ferrous ion, that is Fe2 plus, it has spin equal to 2 and it is going to contribute 4 times mu b. So if you just leave the contribution of residual orbital moment, then we can say that the effective number of Bohr magnetons per Fe3O4 comes up to be equal to 14. That is when all the spins are parallel to each other, because earlier magnetite was considered to be ferromagnetic material. So in ferromagnetic material, all spins are parallel to each other, according to which the effective number of Bohr magnetons per magnetite unit should be equal to 14. So this is from calculation. But when we observe through some experiments, we find that the effective number of Bohr magneton per unit of magnetite, it is just 4.1. So you can observe the calculated thing is 14 and observed one is 4.1. So there is a huge discrepancy. So from this discrepancy we can say, or we can doubt on that whether magnetite is ferromagnetic or something else. And this discrepancy is accounted for if the moments of Fe3 plus ions are antiparallel to each other, then the observed moment will be due to Fe2 plus ions. So if you just consider the spin arrangement in magnetite, that is FeO, Fe2O3, this shows that the moments of Fe3 plus ions cancel each other because they are equal and antiparallel to each other. but there exist the moments of Fe2 plus ions. So we can say that ferrimagnetic material is a material with opposing magnetic moments, as you can observe here. That is something like antiferromagnetism, but these moments are unequal in magnitude. That is the contribution coming from Fe2 plus ion. So whenever the moments are unequal, then we can say there exists some amount of magnetization, which is the spontaneous magnetization within the material. So we are not applying any external magnetic field, but due to this unequal magnitude of spins, we can say that there exists some amount of magnetization within the material. And this inequality is due to only one simple reason, that is the system or the populations consist of two different types of atoms or ions. So here we can observe there is Fe3 plus as well as Fe2 plus. If you just write simply Fe3O4, we can't distinguish between the two oxidation states based on which we can understand about the effective number of Bohr magnetons. So when we consider the oxidation states, we can consider these as two separate types of ions which have different magnetic moments, and some are going to cancel each other because of equal and opposite nature or antiparallel nature, but some are remaining as it is because these are not going to get cancelled with the remaining. So net effect is not zero, and that is due to two different types of atoms present in the material. So that is the main criteria for ferrimagnetism. And all these things are just assumptions, whatever they are told. So there is a requirement of experimental evidence whether this concept given is correct or no, and that is also confirmed by neutron diffraction experiments. So we can say that for a ferrimagnetic material we have the order as unequal and antiparallel. So something like combination of ferromagnetic and antiferromagnetic material. So that is the speciality of ferrimagnetic material. And then let us understand in depth about the concept of ferrimagnetism. So as we have seen, a very systematic discussion of the consequences of this type of spin order was given by Lewis Neal with reference to important class of magnetic oxides which he named as ferrites. So clearly we can say that ferrimagnets are called as ferrites, and these are mainly magnetic oxides. So there is a requirement of oxygen atom if you are dealing with ferrites. And ferrimagnetism has its same physical origin as in the case of ferromagnetic and antiferromagnetic. So if we just look at these spins, then they are parallel and equal to each other, something like ferromagnetism. But when we consider these spins with respect to the earlier one, they are antiparallel to each other. So unequal and antiparallel. Some effect will be nullified, but net effect is non-vanishing. So that is evident from this magnetic order, which is ferrimagnetic order. That's why we can say the physical origin is same as that of ferromagnetism and antiferromagnetism. So in ferrimagnetic material, whatever magnetization is there, that is again caused by the combination of dipole-dipole interaction and exchange interaction, because it has to obey Pauli's exclusion principle. But only difference is that in ferrimagnetic material there are different types of atoms in the material's unit cell, as we have seen. Even if you consider magnetite, which was considered ferromagnetic earlier, when we consider the oxidation states of each ion, that is Fe3 plus and Fe2 plus, those are acting as two separate type of atoms within the unit cell of the material, that is magnetite, which makes magnetite ferrimagnetic material and not ferromagnetic material. So it is something like the specialized case. Ferrimagnetism is a specialized case of ferromagnetism, or even you can say antiferromagnetism. Then moving to its chemical formula, general formula we can say for ferrite is MEoFe2O3. So Me is nothing but a divalent cation. So it is something like a metal. Example, zinc, cadmium, iron, manganese, magnesium, nickel, copper, cobalt. Any kind of a divalent cation can be placed in place of this Me, that is metal. It can be even iron or anything of this kind. So in general we can write it as Xy2Z4 or MEoFe2O3. So Fe2O3 is generally common in case of ferrites. Another thing which we need to remember is that this divalent cation whatever we are having or the metal, it need not always be magnetic. Even the magnetic material like iron, nickel also holds good, and even the non-magnetic materials like copper also goes well. So it is just necessary that it needs to be divalent cation. And this is the general formula which gives all the members of ferrite group. So one example with the crystal structure you can observe here. So there are different types of atoms. This white atom is corresponding to oxygen, and clearly we can observe that iron and the metal ion both are having opposite spins. That is, one is in downward direction, one is in upward direction, and the magnitude is not going to be equal. So if you look here, the magnitudes are also different. So net magnetization is not equal to 0. So about the structure in detail we will study in next class when we study about the types of ferrites. So the term ferrimagnetic was coined originally to describe the ferrite type of ferromagnetic spin order. So it is clear that it is the specialized case of ferromagnetic material. That's why it is also called as ferrite type of ferromagnetic spin order. And when you go for the extension of this term, it covers almost any compound in which some ions have also moments antiparallel with respect to other ions. So when we say antiparallel, we get antiferromagnetism. And generally many ferrites or ferrimagnetic materials are poor conductors of electricity. So when the cases where the antiparallel magnetic moments of two sublattices are not completely compensated due to a number of reasons. Reasons may be the difference in number of atoms or difference in the nature of atoms that make up the two sublattices. So two sublattice model in antiferromagnetism we have already studied. And whenever there is no complete compensation, we can say such phenomena is known as ferrimagnetism. So in short and sweet we can say ferrimagnetism is uncompensated antiferromagnetism. So two naming we got, one is ferrite type of ferromagnetic spin order, another one is uncompensated antiferromagnetism. And again there exists a transition temperature below which we observe magnetization, that is spontaneous magnetization, and the transition temperature is called as ferrimagnetic Néel temperature. So as in the case of antiferromagnetic material, we had needle temperature. Just to distinguish between antiferro and ferri, we are naming as ferrimagnetic needle temperature. And in ferromagnetism, it was Curie temperature. So if we understand about the behavior, external behavior is almost similar to that of ferromagnet, due to which we say it is the special case of ferromagnetic material. But where the difference comes, it is in the internal structure. So there is a difference in their internal structure, due to which again the temperature dependence of their spontaneous magnetization is also going to be little bit different. That's why we say magnetite is ferromagnetic material, and when we get into depth we can say that magnetite is actually ferrimagnetic material. So externally both are alike, but when you go for internal structure based on the study of the moments, then we will understand the difference and we can just specify which type of material that is, whether it is ferro, ferri or antiferromagnetic material. And this is about the brief history, ferrimagnetic order, that is the nature of magnetic moments or spins, then the general formula, what are ferrites or ferrimagnetic material, and nature of it. So in the next class, we are going to deal with the structure or different types of ferrites. So till then, study well and stay tuned for more physics related classes. See you soon and thank you.